In this video, we're going to look at the wave patterns that occur. Now, for the entire video, for each object, the string, the open-ended pipe, and the closed-ended pipe, we're going to look at and say that the length of whatever object we're looking at is always going to remain a constant. Okay, and the symbol we're going to use for it is L. So now, we were discussing before the simplest pattern, standing wave pattern, that can arise on the string. So the simplest standing wave pattern, and if we treat each end, and we are going to as a fixed end, if one of the ends oscillates, you have a pulse, and it's upright. As it hits the other end, it'll reflect inverted. So the simplest standing wave pattern that's going to form here, where you get this thing called resonance, is called essentially the fundamental frequency. The fundamental frequency is the lowest possible frequency, usually referred to as F1. We gave this numbers in class. Here I'll just use variables. And if we look at this, we have one loop on here. So one loop will equal half a wavelength. Alright, just to kind of recall for a quick second, the fundamental frequency is the lowest possible frequency a standing wave pattern can occur. This is also known as the first harmonic. Alright, and again, it has the standing wave that exists on this is half a wavelength. Now, if we increase the frequency in class, alright, and since the string doesn't change, the speed will remain constant. Now, just to look back at the proportionality, if this remains constant and we increase the frequency, the wavelength has to decrease. So, since the string doesn't change, the next standing wave pattern that occurs is going to look like two loops, where the length here will have one whole cycle on it, okay, and this would be one wavelength, and this would be known as the second harmonic, or 2 times the fundamental frequency. So now as we keep going through this pattern and increasing the frequency, the wavelength will get smaller and smaller and smaller because the medium doesn't change, therefore the speed doesn't change. The next standing wave pattern that's going to exist, you're going to have 3 loops. Okay. 3 loops will be, when you look at this, each loop is a half wavelength. If I go through here, I have one whole cycle, then a half of a cycle. So this is going to be 3 halves of lambda. And the frequency will be 3 times the fundamental, and this is known as the third harmonic. So remember that the harmonics are just multiples of the original. And this is what the standing wave, if we keep going, this is what the standing wave pattern will look like. You just add one loop each time. Alright, for an open-ended pipe, you drew this pour flute on here, or a piccolo, if you like to refer to it as. And I'm just crossing out some of the holes here to set up kind of how this thing works. So if you close the holes with your fingers, you end up with 2 open ends here. An open end in this spot, and an open end right over here. So basically what forms at the open end is these two act like an antinode. And in between, okay, depending on what the frequency is, you're going to have your node, antinode, node pattern. Node pattern. And you're going to have a standing wave that exists from one open end to the other open end. Now, to kind of parallel this to the string simulation, this acts as a loose end. So instead of inverting itself and reflecting itself over, the standing wave is going to reflect itself back on the same side. So the standing wave pattern that exists is going to look as follows. On each loose end, on each open end, what will happen is you have to have resonance, so the medium has to be vibrating. Therefore, the air here has to be vibrating a lot, and the air here has to be vibrating a lot. So the simplest pattern that can exist is an antinode, antinode, node pattern. Now below this, the two lines I'm drawing represents a cross-section area of the pipe itself. So if you cut the pipe in half and look at it sideways, you're going to have an antinode, node, antinode pattern, which means your standing wave is going to look as follows. Okay, if you look at this from here to here, would be antinode to node, and that's half of a loop. Alright, and from here to here, it's node to antinode, so it's another half of a loop. Well, if I look at a whole loop, alright, such as I did here, node to antinode to node, the node to antinode is a quarter of a wavelength. So if we go antinode to antinode, this is the length here will equal 1/2 of the wavelength, and this will occur at the fundamental frequency. So now if we continue this pattern, simply having to have antinodes on both ends. Alright, the next simplest pattern we can get here is as follows. You can add a node and an antinode, and you can fit one whole wavelength in here. So if we look at the picture is going to have one whole loop and two half loops. So the length of this will equal one wavelength. This will resonate when the frequency is twice the original of the fundamental. And we can see that as the frequency goes up, the wavelength is getting smaller. In other words, more loops can fit in there. So as we continue to go to the third harmonic, we're going to have an antinode, node, antinode, node, antinode, node, antinode pattern. So looking at this, essentially, if you look, we're adding a node and an antinode. Alright, the length of this will be 3/2 lambda, and the frequency will be 3 times the fundamental, or the third harmonic. So for an open-ended pipe, this pattern continues, essentially each time adding a node and an antinode to the original. Now we're going to look at a closed-ended pipe. Alright, a closed-ended pipe here basically looks at it's a little misleading because both ends aren't closed. You have actually an open end at the top and what's considered a closed end at the bottom. Now, for the open end at the top, you want to hear resonance, so you're going to have an antinode. In other words, the air is going to be vibrating very fast, just like the string is at an antinode. The closed end, you're going to have a node. Okay, now I'm using a Coke bottle here. Yes, that's supposed to be a Coke bottle to, kind of illustrate this pretty. Okay, for the representation, I'm going to draw essentially a cross-sectional area of a pipe, and I rotate it horizontally, just for a little more space. So we're going to have an antinode, node pattern here. Now at this, we're going to look at this and we're going to say, alright, well if it's an antinode, the air has to be vibrating a lot here. And then this is going to come down to a node. So visually speaking, this is what this look like. It'd be essentially a half of a loop. It's not quite a whole loop, it's half of a loop. If I look at this string pattern, I'm going to have a node, an antinode, and a node. So if I go from antinode to node, it is half a loop, which means it'll be a quarter of a wave. So at the fundamental frequency for a closed-ended pipe, okay, the length will be 1/4 of the wavelength. Alright, now as we go to the next standing wave pattern? Well, the next standing wave pattern that could actually exist would be a node, antinode, an antinode, node, antinode pattern. Now if we look at this, an antinode would be at the end of the pipe. This will actually not exist because you can't have an antinode at the end of a pipe. So the next simplest pattern where you have a node at the end of the pipe and an antinode at the top of the pipe is when you have a node, antinode, node pattern. So the standing wave pattern will look as follows, where you have one whole loop and one half of a loop. Well, if I have one whole loop and one half of a loop, this would be L is 3 halves the wavelength. Now it turns out that technically when you have an antinode, node, antinode pattern that doesn't exist here, this would be half a wave and this would be this what's considered the second harmonic. But for a closed-ended pipe, it's going to be odd harmonics only. It will skip the second harmonic and it will just have odd harmonics. So this would be the third harmonic. Mainly this is considered to be a standing wave, but since it does not exist in the pipe, due to the construct of the pipe, you have to have a node at the closed end. That will just happen. So the next pattern, the antinode, node, antinode, node, antinode pattern, will also not exist. Alright, this is when the wavelength is one whole wavelength. So the next simplest pattern here, to have a node at the closed end and an antinode at the open end, will be a node, antinode, node, antinode, node pattern. Alright, and it would look as follows. You would end up getting 2 whole loops and a half of a loop, which means you would have the length is 5/4 lambda, and the frequency is going to be the 5th harmonic. Alright, and that does it. You have string, open-ended pipe, closed-ended pipe. Now you just have to keep in mind, at least for all of them, that the string ends will be fixed, so you have to have nodes on the end. The open-ended pipe would have to be antinodes, and the closed-ended pipe, on the closed end is a node, and the open end is an antinode. From there, if you can draw your standing wave pattern, you're in good shape. Everything can be solved from there.